So, good morning, everyone. Our today's lesson is about an laboratory work dependence of range on angle of launch. The objective of our work is to investigate how the range of projectile depends on the angle of launch with respect to the horizontal. The apparatus of our work, it is the interactive simulations FET called Projectile Motion. FET it's an online simulation system for making the laboratory works in easy way. You need to open the FET in your browser and then find the projectile motion simulation work. This simulation will be looking as shown in this picture. First of all, our introduction. Projectile motion is a form of motion in which an object is thrown near the Earth's surface, moving along a curved path under the action of gravity only. The horizontal range r, or the horizontal distance traveled by a projectile, depends on factors including the initial velocity, v sub 0, and the launch angle theta. The range r can be derived from the kinematic equations and is given by r equal to the v sub 0 squared multiplied by the sine 2 theta divided by the g, where r is the horizontal range, v sub 0 is the initial velocity, and theta is the angle of launch. G is the acceleration due to the gravity. G in the Earth is equal to the 9.8 meter per second squared. This equation shows that the range depends on the sine of twice the launch angle, reaching its maximum when theta is equal to the 45 degrees. Our theory: in ideal conditions, ignoring air resistance, the range of a projectile depends on both the initial speed and the launch angle. When the angle is increased from 0 degrees to 90 degrees, the range first increases, reaches a maximum at 45 degrees, and then decreases. This experiment seeks to validate this theoretical relationship, the procedure of our work. First of all, the first step is to set up the projectile launcher. Position the launcher on the level surface. Use the protractor to set the initial launch lane. In our work, we will use our FETA simulation system. So we're already opened our simulation, and first of all, our simulation will be looking like this. So first of all, you need to put this projectile gun to the level of the surface, to the 0 meters, and set the first angle of 25 degrees and choose the initial speed, for example, 50 meters per second. And then you need to already take this table to measure the range, time, and height of our projectile. So the second is to calibrate for a consistent initial velocity. We will send our angle of our different angles and then making the launches. Start with the launch of 25 degrees and launch the projectile. Measure the horizontal distance traveled from the launch point on the point of impact, recording this at the range r. Then we need to make this calculation. We need to make this experiment with the angle of 30, 45, 60, and 75 degrees, maintaining the constant initial speed for each launch. So every of our launches will be made by the initial speed of 15 degrees, 15 meters per second. And then we need to record our data for each angle and record the average range in the data table. And what's the purpose of our work? We need to compare the real distance with the calculated distance or the theoretical range. We will create this data table where the first graph is the launch angle, the second is the measured range, and the third one is the theoretical range. You need to launch every projectile with every degrees with the same initial velocity and measure the measured distance, our experimental distance. For example, is our projectile with the 25 degrees and the initial speed of 15 meters per second. We need to put this table on our projectile, and we will have our range 17.57 meters. And we need to put this range in our table 70.57 meters. And then we need to make this experiment with different angles, with 30 degrees, 45, 60 degrees, and then 75. and the initial speed is maintaining constant. So our distance of the projectile of 30 degrees is 19.86 meters. We need to put this information in our table. Then the range of the projectile with the 45 degrees, it's the maximum range, which is 22.94 meters. 22.94 meters. Range of the projectile with the 60 degrees is the same as the 30 degrees, 19.86. Then the range of the projectile with the 75 degrees is the smallest range, which is equal to the 11.47 meters. And then, using the formula of the R from the kinematic equations, we need to calculate our theoretical range and compare it to our measured range, and compare the average measured range and average theoretical range, and find our error. So and then when we made our all measurements with our angle and our measured range, we can calculate our theoretical range, TR. So to calculate our theoretical range, we will use formula of TR equal to the V sub 0 squared, which is the initial velocity squared, times sine of 2 theta. So it's the sine of the doubled angle divided by the rotational acceleration. So let's calculate our first theoretical range, TR sub 1. Velocity initial is 15 squared times sine of 50 degrees divided by the 9.8. So 15 squared is 225 times sine of 50 degrees. It's nearly equal to the so then after the calculation, our theoretical range will be nearly equal to the 17.58. So it's not equal to the measured range sub 1. And then you need to make these calculations 5 times, then find the average measured range and find average theoretical range, and then compare them. And so then, after making every calculations and comparing, you need to write the conclusion, where you need to represent the dependence of the range due to angle and the initial velocity, and the absolute error of the theoretical range and the measured range. As your homework, your homework is pinned in the Google Forms, in the Google Classroom. First of all, you need to open our Google Classroom group, and then find the theoretical videos on kinematics. It's your homework. There is the video about the acceleration, the types of the acceleration, and then there is also an acceleration test. You need to complete it, and I will check your answers, and I will give you the right answers and your error work. So the lesson is over. Goodbye.